This lesson is on 10.1 and 10.2. 10.1 is just a basic introduction to circles, including their circumference, and 10.2 is on angles and arcs, specifically central angles and arcs of circles. Much of lesson 10.1, if not all of it, is a review for you. And so here we have a very simple circle with a few things labeled. Okay. I do want to point a couple things out. First of all, this is how we label a circle. We draw a circle and put a dot in the middle, the dot being the center, and it will prevent us from confusing it with zeros or O's. And then we put the letter, which is the center of the circle. In this case, the circle is C. It could have any other letter. It could be the name of the circle. Obviously, a chord is a segment that connects whose endpoints are on the circle. A diameter is a chord that happens to go through the center of the circle, which makes it the longest chord. And a radius is any segment that goes from the center of the circle to the circle. You'll notice that a diameter is 2 times the length of the radius because it's simply 2 radii put together. The other thing that I want to point out is the definition of circle. It's basically a collection of points or a locus of points that are the same distance from a given point. So if this is our center, what all of these points have in common is that they're the same distance from from point C. And that distance is the radius. So despite the fact that we name a circle by its center and we measure the distance from that center, it's not actually part of the circle, only the points on the outside. And nothing else, nothing on the inside, nothing on the outside. Okay, real quick examples here. ST is 18. Well, ST is a diameter, RS is a radius, so RS is going to be half. If RM is 24, RM is a radius, they want to know QM, which is the diameter, it's going to be twice the radius. Obviously, each one of these is assuming a different circle. If Rn equals 2, Rn is a radius, find Rp. That's another radius, so it's also 2. Extremely simple. Okay, this can get slightly more complicated, but it's really not that bad. We just break it down one at a time. The diameters of circles X, circle Y, and circle Z are 22 millimeters, 16, and 10. Find EZ and XF. All I'm going to do in this situation is find one little piece at a time. The diameter of circle X is 22. That means its radius is 11. So EX, for example, would be 11. The radius of circle Y, well, if the diameter is 16, the radius is 8. Circle Z has a diameter of 10. That means its radius is 5. So this is 5. Now, from Y to Z is a radius of circle Y, so it's 8. Well, if this part is 5, this little part has to be 3. And we've gotten everything. We've got it all figured out. We just need to find EZ. Well, E to Z, let's count it up as we go. 11 plus 8 is 19, plus 3 is 22, plus 5 is 27. EZ is 27. And XF, well, from X to Y is 8, to F is 3 more, that's 11. Again, when you encounter a problem like this, you're simply going to write each little part down and then add it up. Okay, this you must remember, you must be able to spit this out and drop of a hat. Do not get it confused with pi r squared. Do not tell me the circumference of a circle is 360. Never, ever, ever. Circumference is length. It is not a degree measure. Okay, there's 2 ways to find it. One is to multiply pi times the diameter, or since the diameter is simply 2 radii, or 2 times the radius, you can use this formula, 2 pi r. Okay, some simple examples. Find the circumference if the radius is 13. Well, the circumference is 2 times pi times the radius, so in this case that's 26 pi. Feel free to approximate that in your calculator if you wish, or leave it alone. Okay, find the circumference if D is 6 millimeters. Well, circumference is pi times D. You can leave it at 6 pi. I kind of want to write the whole number before the irrational one, but that's just me. Find D and R to the nearest hundredth if C is 65.4 feet. Well, let's see. C equals pi times d, right? And if C is 65.4, and then equals pi times d, to find the diameter, I need to divide by pi. 65.4 divided by pi. If you're curious, yes, you could solve for the radius first. I just happen to choose to solve for this first. 65.4 divided by pi, oops, divided by pi. It says to the nearest tenth, that's going to be 20.8. And if they want the radius, I could solve for it the same way I did circumference, or I could just divide, right, the radius is equal to half of the diameter, which is going to be approximately 10.4. Okay, one more example. This one's slightly more complicated, but really, I hope you can see that it's really not that hard. We need to find the circumference. Well, to find the circumference, which is 2 pi r, I need to know what the radius is. They didn't tell me the radius, but they told me this chord right here. Okay, hopefully you've already picked up on the fact that this is a right triangle. And you might notice that this is one radius, and this is a radius. Which means we have an isosceles right triangle, which means these two angles are the same, which means these two angles are 45 degrees each. I seem to remember that the hypotenuse of a 45, 45, 90 triangle is the leg times the square root of 2. Well, if the hypotenuse is 3 square root 2, then the leg, which I'm not going to write leg, I'm going to write r for radius, because the legs are equal to the radius. Clearly, the radius is going to be 3. So the circumference is 2 pi times the radius, which is 3. They want the exact circumference. Well, boys and girls, the exact circumference is 6 pi. Do not approximate this, or you will no longer have the exact circumference. Okay, and the second part of this lesson is about angles and arcs. So first, I want to introduce you to what we call a central angle. Hopefully, you already know why we call this a central angle. Namely, the vertex of this angle happens to be the center of the circle, from which we get the word central. Okay. As you can imagine, or as you're probably aware, if I add up the measures of all these central angles, you'll see that I get an entire circle, one full rotation, which you know to be 360 degrees. We can use that information to solve a problem such as this. They tell us RB is the diameter, find the measure of each angle. You might be thinking we're missing an angle, and therefore we can't solve this. If you're thinking that, you'd be wrong. Because RB is a diameter, it splits the circle in half. So, you might realize now that this side, the angles on this side, these three, add up to 180 degrees, and these two angles add up to 180. Let's go ahead and add these three. I'm going to collect my x's. 8 and 13 and 5 is 26 x's. And now I'm going to collect the other numbers. That's minus 7 plus 5, which is minus 2. They're half a circle. So these three angles add up to 180 degrees. Again, these are angle measures, central angles, 180 degrees. This has nothing to do with circumference. To solve for x, I'm going to add 2 to both sides, divide by 26, and I have x equals 7. It says find the measure of each angle. Okay, well let's plug in 7. This is the easiest. It's actually on the other side, 140 degrees. That means this guy's 40 degrees, right? Because these two add up to 180. 8 times 7 is 56, minus 4 is 52. 5 times 7 is 35, plus 5 is 40. 13 times 7 is 91, minus 3 is 88. Okay, and now a new term to you, arc, A-R-C. It's simply part of a circle. It's defined by 2 endpoints. In this case, I've highlighted this arc right here. And as you can see, the measure of its central angle is 51.4 degrees. Okay, the measure of this arc is also 51.4 degrees. So the measure of the central angle is the measure of the arc that it intercepts. How do we refer to this arc? Well, I refer to the endpoints, E and C, and I draw an arc over them. That's as simple as it is. This case, we call arc EC a minor arc. Minor meaning small, I guess you could say, because it's less than half the circle. It's a minor arc. Okay, and here you see the same endpoints, E and C. This is also an arc, except for it goes the whole way, almost the whole way around the circle. So instead of a minor arc, because it's more than halfway, we call it a major arc. You may have detected at this point that there's a problem. We've already used the term arc EC. Whenever you're referring to a major arc, you have to use 3 letters to indicate that you're talking about a major arc. The middle letter needs to be any point in the on the arc between the endpoints. In this case, the only choice we have is D. So minor arcs only use 2 letters. Major arcs require a middle name, if you will, a middle point. Oh, and I guess I should point out, if I want to know the measure of this arc, I simply subtract 51.4 from 360. So I write the measure of arc EDC is equal to 308.6. Okay, what if our arc is exactly half a circle? It's not minor, it's not major. We call this a semicircle. Okay, so for example, semicircle CD. Perhaps you've noticed that you're not clear whether I'm talking about the top part of the circle or the bottom part of the circle. And so just like with major arcs, with semicircles you have to provide a letter in the middle. So if I want to talk about the top, I'll call it arc CED or semicircle CED. If I want to talk about the bottom, I'm going to call it CFD or DFC, whichever one. And as you're probably aware, the measure of either of these arcs, of these semicircles, is always exactly 180 degrees. If it's any smaller, it's a minor arc. If it's any larger, it's a major arc. Okay, I'm not even going to ask you to write that down because it's obvious. If 2 arcs are congruent, they have the same measure. The arc addition postulate, you can probably guess, but I'll go ahead and make it explicit. So for this particular example, these letters would not make sense for a circle that didn't have this set up. But for this case, if I add the measure of arc DE, that's this guy, and I add that to the measure of arc EC, I think you probably see where I'm going with this. That sum is going to be the same thing as the entire arc. That would be the measure of arc DC. Okay, this is very similar to the segment addition postulate. So let's look at an example. This is actually the same circle we looked at earlier. Perhaps I want to, or in this case, we're going to assume that I want to, let's list the measures of all these arcs. Arc RS is 52 degrees. How do I know that? Because it's the same thing as the central angle. What's the measure of arc UR? Well, we knew that was central angle is 40, so this is 40 degrees. Okay, let's get slightly more exciting than that. What's the measure of arc US? Well, it goes from here to here, and I'm just going to simply add them together. 92 degrees. Okay, what about the measure of UVS? Isn't that the same arc? Actually, it's not, right? US is a minor arc, UVS is a major arc. You can either add these 3 together, or you can subtract 92 from 360. Either way. What about the measure of RTV? Well, let's see. We remember from last time that RV was a diameter. That's going to be 180 degrees. Okay. One more thing from this lesson, arc length. So we've been measuring arc in degrees, and that's typically how we do it. But sometimes you can actually refer to the length of an arc. So for minor arc CD here, you could imagine straightening it, just breaking it off the circle and pulling it straight, so as if it were a line segment, it would have a length. And there's actually a formula for that. Arc length is really, it's just part of the circumference, and you just need to know what part of the circumference to figure out. So the C here tells you the circumference. And the a over 360 tells you whether you need to do it for half a circle or a fourth of a circle. Maybe you're talking about 3/8 of the circumference. In our example here, the length of I'll use red, the length of arc DC, which I'm just going to mark down here for my own purposes. The measure of that arc is going to be the measure of the angle over 300, or the measure of the arc over 360 times the circumference. They didn't tell us the circumference, but they did tell us the radius. So the circumference is 2 pi r. You remember that from earlier in this lesson. And you'll just plug that into your calculator